Here's how this will work. On the left side of the screen, I'll place an evaluation bar denoting how credible a proof seems at each step. Likewise, I'll label each step of the proof using standard chess.com move classifications. So, let's begin. Proof that 1 equals 2. Let A equal B. Classic book move. It follows that AB equals A squared. That's an inaccuracy because I just only had the B swapped to the left side. A squared plus AB equals A squared plus A squared. A squared plus AB equals 2A squared. A squared plus AB minus 2AB equals 2A squared minus 2AB. And then A squared minus AB equals 2A squared minus 2AB. Fairly solid play so far. This can be written as 1 times A squared minus AB equals 2 times A squared minus AB. And cancelling A squared minus AB from both sides gives 1 equals 2. That earns a mistake, and not necessarily because it's an incorrect step. Instead, because we literally stated AB equals A squared in the second line. Attentive readers should quickly notice that A squared minus AB equals 0, so we're just dividing by 0, making the trick obvious. Hopefully we'll see some better plays soon. Proof that the derivative of x squared equals x. X squared equals x times x, classic book move. X times x equals x plus dot 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 plus x for a total of x times. Frankly, that's a great move. It's creative to break down squaring into repeated addition. D dx x plus dot 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 plus x equals 1 plus dot 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 plus 1. And since 1 plus dot 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 plus 1 equals x, it follows that d dx x squared equals x. Honestly, absolutely phenomenal play. That's worthy of being called a brilliant move, earning it a spot in the Alfred Kempe Hall of Fame. Proof that approximately 535.49 equals 1. From Euler's identity, e to the I pi equals -1. That's a little cooler than a normal book move, so I'll call it a best move. Squaring both sides, e to the 2I pi equals 1. It's a little scary using exponents in the complex plane, and we could just start from here, so that only earns a good move. Raising both sides to the power of -I, e to the 2 pi equals approximately 535.49 equals 1. The gimmick boils down to branch cuts in the complex plane, which makes it pretty cool, but still a little scary using exponents in the complex plane. And it's weird raising 1 to the power of -I, so it only gets an excellent move. Proof that 1 equals -1. 1 equals square root 1. Classy book move. Square root 1 equals square root -1 times -1. Square root -1 times -1 equals square root -1 times square root -1. Square root -1 times square root -1 equals I times I equals -1. That's some strong yet simple play. Well done. Proof that 1 is the largest real number. Assume for the sake of contradiction that some n greater than 1 is the largest real number. Inaccuracy, because I just don't like proof by contradiction. Then n squared is strictly less than n, so n squared minus n equals n times n minus 1 is less than 0. Excellent move. However, this implies that n minus 1 is less than 0, so n cannot be greater than 1, and thus n equals 1. That's some fabulous play that earns a great move distinction. The crux of what makes this proof wrong is what isn't said, namely whether or not there actually is a largest real number. But by kicking the can down the road long enough, most readers forget that premise by the end of the proof. Remember that technique for your next written proof. Prove that there exists no a, b, c, n with n greater than 2 such that a to the n plus b to the n equals c to the n. I have discovered a truly marvelous proof of this, which this margin is too narrow to contain. That's a really brilliant move that makes great use of proof by intimidation and appeal to the stick. Wait a minute, hold on. Fermat wrote that proof? I hate that guy. I changed my mind, it's a super blunder now. Proof that 0 equals 1. From integration by parts, the integral of 1 over x dx equals x times 1 over x minus the integral of x d 1 over x. Clever, that's the best move. The integral of 1 over x dx equals 1 plus the integral of x over x squared dx. Then, the integral of 1 over x dx equals 1 plus, well, the integral of 1 over x dx. And thus, 0 equals 1. Honestly, that's a miss. The setup is intricate and interesting, but at the same time, anybody who has ever solved an integral should see what's wrong here. Proof that 0 equals 1. Again, 0 factorial equals 1 factorial. So dividing both sides by factorial, we get 0 equals 1. That's a blunder. That's a blunder. Awful play. Finally, proof that there are infinitely many proofs that 1 equals 2. Recall from the start of the video that there exists a proof for 1 equals 2. That's a book move, although we'll need to adjust the evaluation bar down to where it was at the end of that earlier proof. Assume that there exist n proofs of the fact that 1 equals 2. We'll proceed by induction on the number of proofs. Interesting gambit, let's see where this one goes. As stated, we've already fulfilled the base case of n equals 1. For the inductive step, n equals n plus 1 minus 1, then n plus 1 minus 1 equals n plus 2 minus 1 equals n plus 1. So the inductive step is complete, and thus there exist infinitely many proofs. Brilliant move. That's an absolutely brilliant move. Alfred Kempe would be proud. And with that, like and subscribe.